Yeah, so good afternoon, everyone. Welcome to this edition of the NITheCS Colloquium. My name is Francesco Petruccione, and I'm the interim director of NITheCS. Yeah? Today, we are very fortunate to have as a speaker Dr. Mawande Lushozi, who is a lecturer in the physics department at the University of Cape Town. He graduated with his PhD from UCT 5 years ago, and he spent then some time as a postdoc at UCT, then at the Institute for Nuclear Theory at the University in Seattle, at the Institute for Nuclear Theory in Seattle. I assume it's at the university there. And since then, coming back to South Africa, he joined UCT again as a lecturer. Yeah? And today he will speak to us about some of his research in high energy nuclear physics, and in particular about the fragmentation region in heavy ion collisions. Yeah. So Mawande, please, you're most welcome to share. Sorry, you're already sharing your screen. You're most welcome to start your presentation. And since we are not so many, if the participants have questions, yeah, they're welcome to raise their hand, and we will give them the right to speak. So Mawande, please, over to you.
Okay, sure. Thank you very much, Francesco. It's always a pleasure to give talks to the NITheCS community. Okay, so yeah, I want to share some work that is not that new, but I was working on as a postdoc in Seattle, as Francesco mentioned. This work was done in conjunction with fellow postdocs Isabel Kolbe and Gongming Yu, under our PI Larry McLerran at the University of Washington. Okay, so let me just set the context for everyone. Right? So this work is set in high energy nuclear theory. You know, we all know that matter is made up of atoms, and that these atoms have a nucleus made up of protons and neutrons. You know, we got that far, but these protons and neutrons are also made up of quarks, you know, that are bound together by the so-called strong force. And this is the region of physics that I am interested in, the matter of how quarks interact with each other and all such things. So quarks, I've got a table of them over here. Quarks are held together by the strong force. It's mediated by the gluons as a force carrier. And under normal circumstances, you do not observe free quarks, okay? They come to us, they reach our detectors and colliders and such as bound states, right? And typically they come in two forms, these bound states of quarks. So they come as a matter-antimatter pair, in which case we call them mesons. And sometimes they come in groups of three, right? And in that case, we call them baryons. So they're going to be heavier than the mesons. Collectively, these bound states we call our hadrons. Okay. So as you can see, the mesons come as a pairing of matter and antimatter, and the quarks, the baryons will come as either wholly matter particles or fully antimatter, right? So as a measure, if you're looking for a measure of the excess, the excess of matter versus antimatter, then a good thing to keep in mind, or a good way to tag this, is the baryon number, right? Because this is how you can see this kind of matter-antimatter asymmetry if you're looking for some measure of it, and it'll be an important quantity just moving forward. So again, this is not the whole story, right? These quarks, as I said, are confined, but under sufficient conditions of pressure and heat, you can melt these hadrons into a deconfined state of quarks and gluons called the quark-gluon plasma. Now, a central question, pressing question in quantum chromodynamics is to find the so-called understand the so-called phase diagram of QCD. Right? Much like we know how water will freeze into ice or boil into steam under varying conditions of pressure and temperature, and those phase transitions of of various forms, we in QCD are after the same kind of understanding for nuclear matter now. Since we know we can melt the quarks into a quark-gluon plasma, we want to understand the phase transitions and how they happen and when it is they happen in this diagram over here. Now, in the case of QCD, this phase diagram is understood under a narrow set of conditions, right? It is understood theoretically and experimentally at zero baryon chemical potential, or equivalently at around zero baryon density, and high temperatures. And this is what you get, for example, in the early universe with the Big Bang, right? You get a deconfined state of matter, the quark-gluon plasma, with very low or zero baryon chemical potential, and it's also understood at zero temperature in some kind of way, but everywhere in between, really, this is the subject of study for various theoretical and experimental programs. Part of the challenge with understanding the QCD phase diagram at both finite chemical potential and temperature is that the numerical schemes such as lattice QCD have trouble with what's called the so-called sign problem. The computations become immensely difficult once you introduce chemical potential and finite temperature. And then experimentally, we can also study these in under a specific set of conditions, in heavy ion collisions. That's a high chemical potential, and high chemical potential as well also occurs in neutron stars. But we'll be concerning ourselves over here with heavy ion collisions. How can we understand finite temperature and baryon chemical potential inside heavy ion collisions? Okay, so this is where the fragmentation region comes in. So in general, so just if you look on the diagram on the right over here, this is a schematic representation of the evolution of a heavy ion collision. You start off with colliding two flat pancakes, flat because of Lorentz contraction, and then they then overlap, create then they create in the middle, like they strip gluons off each other, creating a fire tube in the middle, which upon cooling down will then produce the hadrons. So the region between the two pancakes that after they fly apart is called the central region, right? Which will correspond to particles that arrive at the detectors with very low kind of polar angles and low rapidity. This is the so-called central or mid rapidity region. This is well understood the calculations, calculations are highly advanced in this stage, right? In this part of the particle production spectrum. So things like hydrodynamics and various schemes to understand the quark-gluon plasma are normally referred to this central region. And the thing is, for highly relativistic heavy ion collisions, the net baryon density in the central region is essentially zero, right? As shown in this diagram. So all the baryon number is carried actually in the two fragmentation regions. That is, by the fragmentation regions, I mean these are the remnant, the stuff that's not in the fire tube, right? So these are the original colliding participants. They just dump some energy into the central region, but largely the baryons keep moving on in the so-called fragmentation regions, where they're squeezed, the heat up, and then later on, presumably, hydrodynamized, and then will fragment into some kind of debris of hadrons. But this is not known precisely because as of now, the experiments do not have the needed far forward detectors to study the fragmentation region. But in the next coming years, so this is being studied, at least on the experimental side. The ALICE collaboration is going to be building far forward detectors, preferably or hopefully like where we can be able to study the kind of the effects that take place in the fragmentation region. So my work then is trying to understand this kind of stuff on the theoretical side. Okay, so maybe worth mentioning in a heavy ion collision, this kind of separation of fragmentation regions is not the only condition under which you can study a high baryon density system in a heavy ion collision. Okay. One other thing you could do is to dial down the energy of the collision so that there's a maximal baryon stopping, right? So these things don't have enough energy to pass through each other, so all of the energy is dumped. Essentially, all the energy and the baryons are dumped essentially in the central region, and there's no separation of the fragmentation regions. Okay. What you will have then is create a very dense, put all the baryons in the central region, and you can study a very dense, somewhat hot medium in a heavy ion collision. This is the program of the so-called beam energy scan in the Brookhaven National Lab, right? They're trying to study the QCD phase diagram under these conditions. So studying the fragmentation region allows us then to, like in the way that I've described, allows you to do something similar, but also dial up the temperatures a little bit and explore more of the phase diagram. So yeah, let's talk a little bit about some of the ideas involved when trying to talk about this stuff theoretically. So yeah, let's understand what it is that we're colliding. Okay, so it turns out that to study a heavy ion collision on an ultra-relativistic collision, it's best to think of hadrons and the nuclei not as asymptotically free states of quarks there, but rather as you ramp up the energy, your nucleus resembles more and more a dense medium of gluons. Okay, right. So I've got a schematic diagram of this on the right. That shows you that as you decrease the so-called variable x, and which is the same as just increasing the energy of the collision. Your nucleus looks like it's more and more like full of gluons until you reach a state called saturation, which is also rapidity dependent, I guess. So, and yeah, and again, this saturation region is characterized by some emergent scale. It's called the QSAT. Right. So Q saturation tells you the kind of I guess it's the kind of transverse size above which the nucleus will be opaque, really, right? So everything larger than 1/, QSAT in size will collide with the nucleus with a cross section of approximately 1, right? Or probability of the order of 1. And yeah, so these numbers at the LHC will be between 2 and 6 GeV, and at the relativistic heavy ion collider in Brookhaven, you expect this to be between like 1 to 2 GeV, say. Okay, so this, for those who are not familiar with this kind of language I'll be using, I'll be working in the so-called light cone coordinates, which are ideal for dealing with very fast, highly relativistic phenomena. Okay, so I'm just going to flash that for you. And then let's talk a bit more now about this color glass condensate that I was describing. It turns out that, again, this dense gluonic medium, we were fortunate in that the dense gluonic medium then forms what's called the color glass condensate, which means that we have a color field that really behave classically, and the classical in the sense that you don't have to worry, at least in as far as describing the medium itself, you don't have to worry about quantized fields, and these are essentially described by a classical Young-Mills equation that I'm showing you above here. So yeah, this is a very, very localized field, moving at essentially the speed of light. So what you have is a field generated by some frozen-in. That's the picture we have, is of some frozen-in color sources that then generate a classical field. And now let's set up. Now that we've set up a problem, we want to understand the physics of the fragmentation region by going and sitting in the rest frame of one of the colliding nuclei. Okay, so if one thinks about this in the rest frame of a colliding nucleus, then you'll have
Mawande, we can't hear you. Ilya, can you hear Mawande?
No.
Okay, let's give him. Thank you. I'm not sure. Let's ask in the chat.
Apologies. Yeah.
Okay,
we just had load shedding. Apologies.
I thought so. Okay. You need to share again your screen. Excellent. Thank you very much.
Good. Okay.
I'm sure everybody understands because all of us are in the same boat.
Yeah, sure.
At different times.
Yeah. So yeah, again, we imagine in this picture, we imagine you're sitting right on one of the nuclei, right? It's called the target nucleus, and then we, for simplicity, will describe then this target nucleus as just a collection of constituent quarks just floating about, and your projectile nucleus now will be a very highly Lorentz contracted pancake, zooming at you in the diagram above. It zooms from left to right, and it'll then resume then to kick successive quarks, imparting some kind of longitudinal velocity and maybe transverse, but we're going to concern ourselves in this case to restrict ourselves to just motion in the longitudinal direction. So as you can see, what happens as the projectile nucleus moves from left to right, sweeping through the nucleus, it'll knock the quarks closer and closer together, creating a net kind of compression. Okay, and this kind of idea is, existed since the 80s, although in like a more rudimentary kind of way, because they assumed either just these things get some typical velocity that is the same, so you get a kind of a flat distribution of kicks, and our goal in this work, and building on others before, is to take these old ideas and express them in this the now known language of saturation and the color glass condensate and such. Okay, so we want to know, how large is this compression of the nucleus, as the one zooms past us in the fragmentation region, and how much energy will be dumped into the fragmentation region as these fireballs fly past each other, and how does this compression depend on this saturation scale, the thing that characterizes this saturation phenomena in heavy ion collisions. We'll go on then to build. I'll show you how we build an intuitive framework to try to understand the evolution of the fragmentation region. So we'll keep this discussion simple, and that we'll assume a kind of classical color-charged particles constitute our quarks. So these are the so-called Wong particles. Okay, and let's describe them in the following pages. Okay, so yeah, so again, if you want to describe, the color-charged point particle interacting with the field, you have to use the so-called Wong equations given over here. So right now, P is the form momentum of the particle, with the tau being the proper time. And this GQ, describes the color charge of the particle. So it's a vector, kind of a vector in color space. And then the field strength tensor F mu nu is known by everyone, and U is the forward velocity of the particle. It turns out that in the case of a sheet of colored glass, so if you have a highly concentrated, highly boosted field, as we would have in the case of a sheet of colored glass, the minus component of the momentum, right, in our light code coordinates is left unchanged by the interaction. Right? And this kind of work was already done in 2019 and 2020 by McLerran, Paatelainen, and Kajantie, who proceeded to calculate the classical gluon radiation that comes from a sheet of colored glass interacting with a point particle. So we want to take these results and then see what kind of momentum distribution these kinds of ideas predict. Okay. Yeah. So exactly. So if you want to find out what the momentum kick is, it turns out it's given by the formula above, where rho A is the charge, the color charge distribution on the incoming sheet, right? And yeah, so each color charge distribution is sampled from a Gaussian, like in the so-called McLerran-Van Gogh model. And this is standard. This is a standard. This was like the first, first model of in gluon saturation physics, and of the color glass condensate. It was the MV model, and it works pretty well. So yeah. So using then this probability distribution of different color configurations on the sheet, we can then extract a distribution of kicks in momentum that a quark would get. Okay, and it just turns out it's a distribution of that sort, right? And then using the fact that the P minus component doesn't change, we can use this distribution in transverse kicks to derive a distribution in longitudinal kicks, right? The intimately related, and then this is the kind of result you get. You get that the longitudinal kicks in momentum that you get is just described by an exponential, with the average given by Q saturation squared over the constituent quark mass M. Yeah, and then now we can try to understand what happens to a distribution of charges, kicked with such a Z distributions of momenta. So I have over here the one particle distribution of that you can derive, right? We discussed this in our paper of 2 years ago, how to build this up step by step. So yeah, you see that you have a component. You have a component over here that describes what happens before the state of the system before the quarks are kicked. Again, we assume like a uniform distribution of quarks, and then the other piece describes the subsequent evolution of quarks after each quark has been struck. So it's the stuff behind the kind of the light front, and we can draw this and see what actually happens. Yeah, indeed, if we look at this, we've drawn the evolution of the quark distributions in as I guess at various at varying times. Varying time is a function of the we're varying time in units of the kind of longitudinal extent of the target nucleus, which we call R. And you can see this is where the sheet is, and there's a pile up in density over there, and then the sheet subsequently moves over here, and then this is the new distribution, and you can see that there's very high density near the sheet, so you get that compression as we promised. Okay, so let's dig a little bit deeper into this this compression. Okay. Sorry. Yeah, I'll dig a little bit deeper, but let me first jump into like another issue of baryon stopping. So, yeah, as in the previous slide, I showed a matter distribution or quark distribution at the end z, but we can change our variables from z, the coordinate z and t, into the coordinates of space-time rapidity, and as well as proper time. And then in doing so, if I look at what happened to the distribution at large proper time, they all settle down into, they settle down into some kind of universal distribution that takes the form shown above. And this is, very interesting because it's strikingly similar to the schematic diagram I showed in I guess one of the earlier slides of the distribution of matter and radiation. This is they kind of settle into that kind of distribution over here. It's a function of rapidity, space-time rapidity, which at late times is of course the same as the momentum space rapidity. And what you see is that as you increase this parameter P bar over M, which is the same as increasing the saturation scale, which is essentially the same as studying higher and higher energy collisions, you get what is expected. Okay, so your distribution started off with a rapidity of 0 because it was at rest, and for a collision of some energy, right, corresponding to the ratio P bar over M is 10, and which we calculated to be around the RIC, relativistic high energy collider energies, you get a net rapidity shift of between 1 and 2. Okay, and as you ramp up the energy, so P bar over M of 70 corresponds to roughly the energies you find at the LHC. You see, you get again a rapidity shift of around 2 units. And the general result for these rapidity shifts is like something that goes like that exactly, but then that advances as the logarithm of saturation scale over M, M being the constituent quark mass, and this is interesting in that in a review paper in 2018 by Buza et al. And also there's a paper written in 1984. But using quite different geometric arguments, they reach similar conclusions that in an ultra-relativistic collision, the nuclei would lose 1 to 2 units of rapidity. Okay, and this doesn't change much from collider to collider because it goes like the logarithm of the Q saturation there, which is essentially like a logarithm of the energy of the collision. And I guess another interesting finding that we got is that it looks like this distribution, it doesn't matter how large you make the energy, like there's a kind of a net maximum height that they go to that is of that form. It's 2 n E minus, where n, I guess for us is the number of valence quarks in the nucleus. Okay, so let's go back to discussing compression. Like, okay, it looks like we saw some compression in a couple slides ago, but yeah, the question is, how much of this compression is real, and how much of this is just the fact that I've knocked my nucleus and it's going to have some Lorentz contraction there. So, is it really compressed or am I just witnessing, will this all be undone by Lorentz contraction? Yeah, in order to answer this, let's study the local velocity of all the particles that are struck. This information should be already in this one particle distribution that we calculated. And from that, we can find that the average velocity at a given point is, given by such a formula. And then using the average velocity, then I can try to find what the co-moving density is of the fluid, right? So to undo the effects of Lorentz contraction. So I divide by 1/gamma, right? And then I'm going to restrict myself to times like while the projectile nucleus is passing through the target, because this is where you get the maximal compression. After the two nuclei separate, you will no longer get the effects of compression. This stuff will just now begin to expand, hydrodynamically or otherwise. So what you see then is that the maximum compression actually is a function of the kind of a Z/T, and it peaks, right on the light front. Okay, like where the sheet is, as expected. But what's surprising was that we could take this limit. It didn't go to infinity. Okay, and maximal compression turns out to be given by this factor over here. This is the maximum density you get, and then so the compression factor is then this square root over here, which goes like Q sat over M, and at the LHC energies, plugged in the numbers, this means you achieve the compression of 10 to 20 times, by a factor of 10 to 20, right? This is in the longitudinal direction. And I mean, the transverse, we imagine the transverse motion will not matter as much. So that means that we have densities at the LHC. If we study the fragmentation region, we claim that will be 10 to 20 times ordinary nuclear matter density. And at the relativistic heavy ion collider, we imagine this compression will be, like a factor of 5 to 10 times. And yeah, again, it's interesting to see that in the review paper by Buzano and et al., they cite this factor of 5 to 10 as well, using very different arguments. So that's it for the work that we've done. Let's look back on what we've done. We used this MV model of the color glass condensate to calculate what the distribution of transverse momenta, longitudinal momenta are. And we use that to describe now the evolution of distribution of valence quarks, and understood what the compression of the nucleus looks like in terms of Q sat, and also baryon stopping, and found that how we change in the sense of this saturation momentum. So, and the question of, okay, do we have a high enough, do you squeeze this target nucleus hard enough to indeed form a fireball of quark gluon plasma in the fragmentation region? I would say yes, because in the you know, just comparing to the bag model, the bag model of I guess it's called the MIT bag model of confinement. It predicts like that the densities of about five times normal nuclear density. You should get some deconfinement and have form a covalent plasma network. Right? So okay, this is obviously incomplete. It's you know, leaving aside that it's a classical kind of calculation for we also need to understand the gluon radiation that will accompany this compression, right? So you produce a high energy density by compressing the baryons, and then you also produce high energies from the gluons that will be radiated as the quarks are struck by this sheet. This is work that has been done partially by McLerran et al. In 2019 and 18. You know, but we have to understand a little bit better the effects of high, of high energy gluons. There, like when you can no longer ignore like the kind of recoil effects when these quarks are struck and the gluons are emitted. This is work I am trying to, disentangle, and this is what I'm working on right now. And when it is done, then I can probably tell you something more concrete about what the actual energy density is, and maybe then what kind of temperatures and densities you can expect, or temperatures and baryon chemical potentials you can expect in the initial stages of heavy ion collision. And also ongoing work is to understand, okay, how will these results change then if you assume non-central collisions, okay? If you got fewer and as you get fewer and fewer participants, how will these results change? Yeah. Anyway, yeah, this is exciting because the experiments coming up soon. I guess in 2027 is when focal aims to be online, and then we can actually begin to put our ideas to the test versus experiments. Yeah, so that's my talk. Thank you very much.
Mawande, for a very interesting overview of your research. Thank you very much.
Thank you.